Okay, so it's the last day on Friday. It's a little noisy in the hallway, so if you hear a little extra noise there, I apologize. All right, just cleaning up some stuff from last class. Now, what we're going to be talking about today are oscillations. Okay, specifically, a lot of simple harmonic motion. Damped harmonic motion will be something we might take a quick look at, but we won't get caught up in it too much. There's just a couple of things that we need to talk about as we go through. First of all, I'm going to do some demonstrations in class. Okay, remind me on Monday that we need to have. I need to show you some demonstrations so that you can really kind of see what's going on with it. I could do a demonstration here, but it's a lot better if you're actually there to see the demonstration. So now, first of all, real simple demonstration of what we're doing here. Okay, I'm going to use it as a vertical spring, which actually is a little bit harder to take a look at, but it does have the advantage of a lot easier to make, maybe not as easy to analyze. Okay, this mass is going to go up and down on the spring. The spring has a spring constant K. Okay, this has a mass M. Okay, this will be my equilibrium position. Okay, it can go up to a point here where it's a lot less coiled. This would be M. So this would be my amplitude. I'll call that XM. It's getting a little crowded in there. So I'll put this over here. Okay, that's my amplitude. It'll go up from this. This is just like a time series picture. Okay, it's going to, we have it here. It's going to go up to this point, and then because a little bit of symmetry, okay, I'll go down to this point, and this distance is also xm. This is just you could call this, if I call this 0, this would be positive xm, and this would be negative xm down here. Okay. The absolute distances here are both xm. That's the amplitude. Okay, so we're going to call xm the amplitude. Now, the couple things that we have to consider when we go through this.
Joe Spiro, please report to the main office. Joe Spiro to the main office.
The time that this takes to make a complete cycle, between going from here to up to down and then back up again. Okay? So if I said that this would be, it gets back to this position. Okay? This would be the time of one period. Okay? So now I'm going to call capital T, that's going to be your period. The time for this to occur is equal to capital T, from here to here. So the time that it takes to make this complete cycle is called the period, capital, and we denote that with capital T. Okay. The number of times that this happens per second, we call the frequency. Frequency is equal to 1 over the period.
Mrs. Price, please call extension 1203. Mrs. Price, please call extension 1203.
Period is measured in seconds. Frequency is measured in 1 over seconds, which is equal to hertz. Okay. So now, what we want to do is come up with a term. We're going to look at what's called angular frequency, omega. Okay, and we've talked about angular motion before, but this is talking about it in terms of periodic motion. Okay, we want to see how often it is that it takes to repeat. Now, basically what we want to do, we know that it's going to be in the same place 1 period later. Okay? So now, if I say, okay, the location of this, okay, we're going to say at t equals 0, switch markers here. At t equals 0, I'm going to say x is equal to xn. Okay, so it's going to start off right here. Goes down, okay, goes back up again. But at t equals 0, x is equal to xn. So now, there's some, that's what I want to make sure that I'm going to say x is equal to the displacement as a function of time. Okay. At its maximum point, at t equals 0, I've got xn. Okay. Now, what function do we have that's periodic? It kind of goes up and down. That's kind of cool. Okay. So now, it goes up and down. Then, okay, but it starts off at its maximum value. It's periodic and starts at its max. Okay, that's going to be cosine. Okay. So x of t is going to be x max times cosine of something. Okay. In general, we're going to say that this is what's called omega t, little t, plus a phase angle phi. Most of the time, we won't deal with the phase angle. Okay, you do have to take into account, but most of the time, we can set the initial position at its maximum point. We can start counting time when it's at its highest point. So then we can just say, well, phi equals 0. Sometimes we can't. We have to leave it up there. Okay. Now. So what we're going to do here, okay, is we're going to look at a time. We're going to say that phi equals 0. And we're going to look at a time ahead when it's repeated itself. So we want to understand what omega is. Okay, we want to know where this omega comes from and how it relates to time. So now, if I say phi equals 0, because it's an angle. So I want to know when this repeats itself. So I'm going to say x of 1 of t is equal to xm cosine of omega t. I'm going to say sometime later, x2, and this is going to be at t plus 1 period later. This will equal xm cosine of omega t plus period. Okay? So it's omega t. This is omega times the time. This time is at whatever this time was, plus the period. Well, my whole point in doing this is saying that 1 period later it's going to be at the same spot. So these two have to equal each other. x1 has to equal x2. So what this is saying is that xm cosine of omega t has to equal xm. Let's shift that over a little bit. Xm cosine of omega t has to equal xm cosine of omega, I can just pull that out, t plus, squeezing here, t plus t. Should fit on there. I'm not confident that it does. Okay, these two have to equal each other. If these two equal each other, x1 and x2, then these two have to equal each other. So now, the xn's will cancel out. Now, cosines equal each other, okay, when it's gone through a period of 2 pi, when it's gone through a period of 2 pi. So now, this omega t, omega t plus that, plus period, has to equal omega t plus 2 pi. Cosines equal each other when it's gone through 2 pi radians. So now I have omega t plus omega period is equal to omega t plus 2 pi. Omega t's here drop because you just subtract omega t from both sides. This means that omega is equal to 2 pi over the period. Or omega is equal to 2 pi times the frequency. So omega is equal to 2 pi, well, you don't need to do it more. Okay? 2 pi over the period, 2 pi times the frequency. Okay? So now, a couple things that we're going to go through very quickly on this. So we know right here, this is kind of the key point. Okay? This is our key equation. So if x of t is equal to that,
Mr. Carmen, please call attention 1206 or come to the main office.
v of t is going to equal the derivative of x of t. Okay? Or however you want to write it. So now v of t is equal to, all right, you have to take the derivative. All right? This is going to be x max. So you still have xm sine. Derivative of cosine is sine, negative, of omega t plus phi times the derivative of what's inside. So now, the derivative of this with respect to time, this is a constant. Omega t, so I've got negative omega xm sine omega t plus phi. Acceleration is a function of time. This is going to equal the derivative of velocity with respect to time, or write it dv dt. So my acceleration as a function of time will equal the derivative of this. So I've got negative omega xm. Derivative of sine is cosine of the arc omega t plus phi times the derivative of this. Again, phi is constant, derivative of omega t is omega, so this is negative omega squared xm cosine of omega t plus phi. One thing to point out, that can be helpful, especially when you're talking about multiple choice. This is xm cosine omega t plus phi. This is negative omega squared xm cosine omega t plus phi. A of t is equal to negative omega squared xm cosine omega, all that. This is just x of t. Okay. This can be helpful and save you some time. A couple other things to point out about that, though. Okay. Acceleration is equal to omega squared times x. So this is very similar to acceleration equals omega squared r when we were doing simple uniform circular motion. Okay. So now we can figure out from first principles now what the velocity is at any moment in time. We can figure out what the acceleration is. Therefore, we can also figure out what the force is as well, which is going to come in quite handy. Let's see, where do I want to go to? 15.3. Okay, I'm going to take you up through 15.4. Okay, now the force law is simple harmonic motion. Now, one thing that we should point out, that beep was just for, because they wanted to. So now, F is equal to ma. So now, the force as a function of time now on this, we can say is negative m omega squared x of t. Okay? This is like very similar to centripetal force. F is equal to m omega squared r. Very similar. Or you could write out what the whole x of t thing is as well. Now, when you're dealing with the spring, okay, when you're dealing with the spring, we know, okay, especially like this, mass attached to a spring that's got a spring constant k here. Okay, we know that the force has to equal negative kx. Well, now we have a new way to figure out what k is. I've got x here, force and force. So now, what this is telling me is that k is equal to m omega squared. So now, k is equal to m omega squared. This is basically the force per unit, force times the per unit length when we stretch a spring. This is the mass, this is the rate of that it goes back and forth. So we now have a way of relating the stiffness or the stretchiness of the spring to the rate at which the mass will go back and forth. Okay, that's incredibly useful. Another thing that we can point out here, sometimes we see it written like this. Omega is equal to k root k over m. Okay. Now, yeah, probably should do it this way too. So if omega is equal to root k over m, okay, we could say that the frequency, so 2 pi times the frequency is equal to root k over m. So if we wanted to look at frequency, frequency is equal to 1 over 2 pi root k over m. And then if we wanted to do a period, which is reciprocal, 2 pi root m over k. Okay? Because going from frequency to period, we just take the reciprocal. Okay, so true. Everything energy. All right, now energy in a spring. This is just be one more of those times where we see cosine squared equals 1. Okay, when you're dealing with this going back and forth, okay, when it's at equilibrium, okay, in other words, it's not stretched or compressed, okay, x would equal 0. There's no potential energy. When you push it in, when you stretch it out, now you have a certain amount of potential energy. Okay, the potential energy of the spring is going to equal 1/2 kx squared. where when we can say this, potential energy is equal to 1/2 K, and X is if we want to look at it as a function of time, 1/2 K XM cosine of omega t plus V. Kinetic energy, by the way, is equal to 1/2 mv squared, which we can also do in terms of time. Maybe sort of a little bit. So kinetic energy is a function of time. We equal 1/2 m. We'll go with. I have to kind of put this in parentheses here. V is a function of time. M omega squared xm squared sine squared omega t plus t. Okay, all I did was square what the I squared v. Okay, we had v from before, omega squared, xm squared. Okay, now yeah, this is x squared, so this should be 1/2 k xm squared cosine squared. So now I have 1/2 m omega squared. Sorry for a second, just take a look at this real quick. All right, so now we know that m omega squared, this m omega squared here, that's equal to k. So k as a function of time will be 1/2 kx squared. So my kinetic energy is a function of time. M omega squared is k, 1/2 k xm squared sine squared of omega t plus v. So now my total energy with the spring is going to equal k plus u. And we'll say as a function of time as a function of time. Let's make this as a function of time too. Something very interesting should pop out of this. My energy is a function of time, assuming no friction. Here's the thing, shouldn't change. So now, k is going to equal 1/2 k xm squared sine squared of omega t plus v. Potential energy is equal to, and I have to wrap it around, u will equal 1/2 k xm squared cosine squared of, wrap it around, move it back a little bit, 1/2 k xm cosine squared of omega t plus v. All right, this is one of those that you don't necessarily have to write everything down on. It's proof that it's got a lot to it. Okay, but now, you guys have been in pre-calc and calc and algebra 2 and calc 2 and everything else like that. You've seen this so many times. Believe it or not, even though you don't see maybe these arguments in front of it. Sine squared plus cosine squared equals what? It equals 1. So now, what I can do is factor that out. My energy as a function of time is equal to 1/2 k xm squared. So now, this is saying that my total energy is equal to 1/2 as a function of time is equal to the spring constant times the amplitude, which is the maximum point. That's a constant. My energy as a function of time is a constant. My total energy as a function of time is a constant. Okay? It's Friday. I think that's enough. I'll see you guys on Monday. And I will have some homework for you. Oh, you know what? I'm going to assign some homework now. Just on these few sections here. So now, your homework. Let's see here. Let's go with 6, 10, 6, 11. 21. Let's go 6, 11, 21. This will be due on Monday. Okay? This is chapter chapter 15. Okay? 6, 11, 21. Can something else make noise? Okay. 25. And then I want you guys to take a look at, so 25 is the challenge problem. Okay. 31 I like a lot. 31, 35, and 37. So I'm giving you a lot of odd problems, 31, 35, and 37. I want these, at least the skeleton of them, in class on Monday. This is due Monday. Okay? You do have a test on Wednesday. Have a good weekend, everybody.